All right, good morning for pre-calculus. So today, the long-awaited logarithms. Okay, so I realize we're going to get to do this not next week because that'll be a review week, but we're going to get to do this again and revisit it the week after that. So that's always a good thing. So the idea of the way the logarithm is written, okay, is we write it out, y equals, right function equals log, and then we have a base, and then we have an argument. Okay, the argument is what you're taking the logarithm of. This base is exactly the same base that we learned in exponential notation. So this is the same base with exponential functions. It has the same rules. Okay, b has to be greater than 0, but it can't be 1. All right. Now, one of the reasons why this is so confusing is because it's well, there's a couple of reasons, but one is that this is 16th century technology and 16th century notation, and we're still using it. So if you ever go back and if you ever had a class in Shakespeare or something, there's an effort to figure out what they're talking about. So it's the same kind of a thing. They put things in an order and in an arrangement that doesn't seem normal to us, but we're looking at it with 21st century eyes, not 16th century eyes. Okay, so I'll tell you a little story about logarithms before we get into dissecting this thing. When I was in younger grades, they had to take me outside and do flashcards, and I had to get like extra tutoring and all that stuff with the math because I was not that good at it. And I remember seeing a square root in the flashcards, right? I mean, it was the easy one. It was not a hard one. And I was like, ooh, what's that? He said, that's not for you. Like, okay, well done. Squash a child's curiosity. You've done it very well. So that's good. But they also eventually ended up with like log of 100. Okay, it was a Catholic school. They the K through 8. Those were the cards we had, K through 8. So I saw that and I was like, what is that? And I said, it's an exponent. And I said, what's that? I'm like, go get to it. Don't worry about it. Okay, thanks. But I always remember like it's an exponent. And they didn't lie to me. I mean, it was a crummy answer, but they didn't lie. And what they're really saying with this is the logarithm, the answer to the logarithm, this thing is an exponent. Now, I know it doesn't look like one because it's on the baseline, but what we're doing here, okay, is that we are taking, let me write it the forward way rather than this way. I should say the backwards way, I guess. Let's go with, yeah, we'll stick with that until we need to make a note. So we have log of b, the log base b of our argument is equal to an exponent. Okay, now here's the 16th century magic coming in to help us out here, okay? B to the y is equal to the argument. All right, that's the equivalent exponential form here. All right, so we're not going to evaluate anything just yet. We're just going to write these two forms and say this is what's going on. All right, let me do a couple that are pretty easy to kind of sort out before we go into doing a lot of these things. But if you just have nice easy numbers, okay, and there's 3 kinds of logarithms that we get to learn. There's 3 kinds of logarithms that you probably maybe have on a calculator. One of them is log base 10. We just abbreviate that with log. Okay, that's what that means. So if you just see log like on your calculator, this guy written right here, log, means log base 10. Notice the second function is 10 to the x. Okay, if you can see that. So that's how to undo it. That's the backwards way. Okay, so it's log or 10 to the x. Okay. Log base e, right? That's called the natural log. Okay, we talked a little bit about e yesterday, and the reason we like we call it natural is because in calculus, you don't have to put in a scaling factor. Okay, so when you do calculus on this, it's clean. There's no scaling factors. There's no extra stuff that comes along for the ride here. It's very clean. And because you folks live in the 21st century, we have log base 2, which is abbreviated LG. All right. Now this one, not in the book, and you probably won't see this until you're like in maybe electrical engineering or computer engineering. But since computers use a lot of 2's, we have a logarithm pretty much for those 2's. Okay. So they will probably not show you this notation in our book. Actually, I know they won't show us this notation in our book, but if you ever see it, that's what it means. Okay. So with log base 10, right, for the easy numbers, all we're really doing, right, is we're saying, okay, well, what do I need to raise 10 to, right, in order to get to 10? So 10 raised to what power? 10 raised to what power equals 10? 1. Let me put in 100. 10 raised to what power equals 100? Just 2, right? 10 squared. Log base 10 of 1,000 equals, right? 10 raised to what power equals 1,000? And that's going to be 3. So if you have really easy numbers here, you can do the logarithms just by looking at it, right? So if I asked you log of 1,000,000, right, without doing this, what would your guess be? I'm pretty certain your guess is going to be 6 because you're going to say, hey, we're just kind of counting the zeros, aren't we? Yes, you are. That's exactly what you're doing, is you're counting the zeros. Okay. Now, log of 20, there's going to be some decimals. Okay. Log of 50, there's going to be some decimals. But if we just go with 10, 100, 1,000, 1,000,000, these are very easy logarithms to take. And the whole point of this is to introduce the tool to you, introduce the logarithms to you, so they don't seem as scary, and it seems like you would want to use them. Why would we want to use a logarithm? Well, there are certain things in sciences that are very different from each other. They're kind of classified in the same classification, but the numbers that describe them can be very far apart. So if you look at, say, if you're in astronomy, if you're looking at masses of suns, right? You know, we could talk about, you know, our sun, but then, you know, I think that's like 1 solar mass or something, right, is a sun. And then there are some massive stars. They're like, you know, 1 times 10 to the 22 size of our sun, or 1 times 8 to our sun, right? It's you know, 1 times 9 to the sun, 1 billion times bigger than our sun. And you might want to put some of those numbers, right? Maybe you're measuring distances, maybe you're measuring, you know, how much light it has. Maybe you're measuring lifespans. You want to put these all in one graph. Well, I don't want to put 1 and have to make all these tiny little marks until I get to, like, you know, 1 billion, right? I don't want to do that. So we just use a logarithm graph instead of a regular graph. And that allows us to put, you know, here's 1, and I know that's 1 times 10 to the 1. Here's 2, I know that's 1 times 10 to the 2. 3, that's 1,000. 4, it's 10,000. Just like we did up here. And you're making a graph, so you're trying to make it easy on yourself. So of course you're going to use numbers that are easy. Okay. And then whatever you have on the y-axis, whatever we're measuring. But the people that do biology, right, you study viruses, you study bacteria, maybe you want to put those on the same graph as a size, and we have to go in the other direction. Okay, we have to go in the other direction. So if I ask you, like, what's the log of 0.1 or 1/10, right? 10 of 1 over 10. 10 raised to what number equals 1 over 10? And that would be 10 to the negative 1, right, as a reciprocal. And the same idea, if we have log of 100, log base, don't do log base 100, we'll get to that. Log base 10 of 1 over 100, right? that is, what is that going to be? And it's 10 raised to what power equals 1 over 100. And you said, well, I got to get a reciprocal in here, so it's a negative. And then if I square it, that should give me, okay, so we're here. Okay. So if we're dealing with very small numbers, right, we're going to have -1, -2. This is 1 over 10. This is 1 over 100. Okay. So if you need to have, you know, very small numbers and you want to compare very small numbers with each other, you're going to be on the negative side of this graph, which is fine. Okay. But the idea here is it's supposed to be a tool for you to use, okay, especially if you're a science that studies things that have you know, a lot of numbers that are, things are very far apart, right? I don't know offhand how big a virus is compared to a bacteria, but I do know they're substantially different. So if you're trying to measure like how big something is, you know, you're going to be using a logarithmic graph in order to describe that. Okay, so that's why you would want to be using this stuff. Okay, and again, if it's up to you, if you're getting to make this, choose numbers that are going to make your life easy. Okay, now in physics that tends to be more of a E kind of numbers, again, because we want to do calculus on it, and we don't want the scaling factors. But pH is log base 10. Chili is log base, how hot chilies are log base 10. So the Scoville chart is base 10. So most things, because we have 10 fingers, are base 10. And you would set something like this up. All right. So you don't have to have base 10. You don't have to have base E. You don't have to have base 2. You could have base anything you'd like. All right. One of the reasons I actually do rather like your book is they don't spend a lot of time on bases that aren't the easy ones. Okay. The book that I remember using, we spent an awful lot of time dealing with logarithms of weird bases, and quite honestly, outside of a math class, like, unless there's a good reason to pick it, you almost never use a logarithm that isn't E, 10, or 2. Okay, those are your logarithm bases, period. You would almost never pick a different one. So with that being said, we're going to pick a different one. Okay, but all we're going to do here is we're just going to get the idea of writing the exponential form and the logarithm at the same time. We're not evaluating this. We're not trying to do anything with this. We're just saying, okay, well, if I was going to write it, what would this look like? Okay. So if I want, say, log base 5 of, say, 25 equals what? And this is the equivalent form, okay, of 5 raised to what equals 25. Okay, and I'm doing that. I mean, I want to pick easy numbers. I want to pick the easy stuff because I want you to say, well, that wasn't too bad. Okay, clearly that's 2, and that's what we're going to do is we're going to replace the question mark with the 2. All right. So if I do, you know, how about log base 3 of 81, right? And 3 to the third, that's going to be 27. 27 times 3, that's going to be 81. So it's 3 to the fourth. And the equivalent exponential form here is 3 to the fourth is equal to 81. Okay. And there's a lot of times when they've got some crazy base under here, and like I can't just look at it and tell, I don't know. We got to convert it because this way I can think, and this way I can't. Okay. So it's a lot easier for me to kind of put it in this position and think, okay, 3 raised to what power is going to give me this thing? Okay. So how about something like, oh, let's see. How about log base 4 of 8? Okay, this is a hard one. So maybe, you know, that's why we would need to do this, right? 4 raised to what power equals 8? Well, if I square it, I'm going to be at 16. And I got to divide it in half, and that's not an operation we could do. Okay, we have to do a power thing. So no dividing, right? No adding, no dividing, no multiplying. Well, multiplying, but only itself. We need powers of 4. Well, you know, I can get 2. 2 to the third is equal to 8, right? Oh, but how do I get to be 2 out of 4? And if I took maybe 3/2, where I take the square root of 4 to get 2, and then 2 raised to the third power. Or 4 cubed is going to be 64, and then take the square root, and that's how we get 8. So I don't know, I would not be able to look at this and just say, oh, well, obviously it's going to be 3/2. Like, no, that's not obvious. Okay, that's something you got to spend a lot of time thinking about. Okay, so this way, thinking about it, like 4 raised to what power might be 8, like that's an easier thing to think about than, it's effectively the same question, right? 4 raised to what power is equal to 8? But thinking about it in this circular thing is kind of weird. Thinking about it this way is pretty easy. Okay, considering, comparing. I think these are like the hardest ones they ever have you do. All right, and that's how we go through and deal with that. Okay, so maybe 1 or 2 more. Okay. Oh, how about this one? The log base 1/5. Okay, there we've got a fraction in here. That's in the rules. It's not a 1 and it's bigger than 0. And we're still going to say something like 25. Okay, so 1/5, this is equivalent to, right? 1/5 raised to what power equals 25? Well, the first thing I got to do is I got to flip it, right? So that's an inverse, it's a negative. And then if I squared it, then that would, okay, if I squared it, that's going to do it. So it's going to be -2. This is going to be -2 here. Okay. So when you've got these really crazy bases, like I'm not going to think about it this way. I'm going to move it over to an exponential form and think about it that way, because I'm used to thinking in exponents. I'm not used to thinking this way. Okay, you can actually get used to thinking like this, but generally not so much. Let's see, what other crazy thing can we do here? How about log? We'll stick with 5s. How about we do the log of the base square root of 5 of 125? Okay, this is crazy. Okay, so the square root of 5 raised to what power equals 125? Well, the thought goes, right, 5 cubed is equal to 125. And then we have the square root in here, right? So we've got to double this. So the square root of 5 raised to the 6th, right? Because what we're doing here is we're saying the square root of 5 squared cubed, right? And when we have the exponents arranged like this, we have exponent to an exponent, we multiply them together. That's how I got that 6. So I went square root of 5 squared to get the 5 raised to the 3rd, and that gave me that one. So that's going to be 6. So my equivalent exponential form, right? Square root of 5 raised to the 6th is equal to 125. Right. So I know that is a bit crazy for all of these things. There's not. So here's when I write problems. Okay, I'm still coming to terms with the 21st century and writing problems for online instruction because, yeah, that's harder. Usually, what I would do is maybe I have a five-part question, right? One question with 5 parts, A, B, C, D, and E, and it's going to look exactly like this, where 3 of those parts or 4 of those parts are going to have numbers that look like this, with this is the hardest one here, but they're going to look like things like, hey, what's log base 4 of, I don't know, 512 or something, okay? Or it's 2 to the 9th. Log base 5 of 625. Okay, I'm trying to be sneaky, but I'm not doing a good job here. Okay, so most of because the whole idea is like, do you understand what this notation means? So you're going to have, of those 5 problems, you're going to have 3 to 4 of them. They're going to look like this, and then one of those 5, 20% of that is going to look like something crazy like this. So the thought on my part is, even if you're like hanging on and you're like, okay, I kind of get this, and then you're like, okay, I give up. Like, I'm not doing this. okay? You still get an 80% on that question. And if you just maintain that level, then that means you get a B for the test. So that I'm pretty happy with the fact that you can hang on here. I think that's a B. That's pretty good. And maybe you don't get the last one. All right, you're not great. It's fine. Okay, but you're pretty good, and that's, I think we're all willing to live with. I got an 80%. Okay, and there's other questions. You'll make that up. But that's the kind of thing I get. So you're not getting like 20 of these, because no, I don't want to do 20 of these. Why should I make you guys do 20 of these? And it's not useful. This is not a skill, right? This is not a skill that's going to work out for you. You might come across a system where it's better to count in 3s or 5s or something. But, you're never going to count. You're never going to need powers of 1/5. You're never going to need square roots of pi bases or anything. That's not happening. Okay. So let's see if we can graph one. Okay. Let's see if we can graph a logarithm. So graphing. Okay. Here's the secret of graphing a logarithm. Logs are inverse functions to exponents. So if I was going to go through it, we were just going to say, do a square root graph, right? I was going to say y is equal to the square root of x. And we draw a little t-table here. What numbers are you picking? I'm picking 0 and 1, but I'm not picking 2, am I? I'm picking 4. And I'm not picking 3, I'm not picking 5. I might pick 9. Why did I pick these numbers? So I put them in the square root. I know what's going to happen. It's almost as if I picked y's to be 1, 2, 3, and then figured out what my x had to be in order to get to this, didn't it? And that's exactly what we're going to do with the logarithm. We're going to pretend that we're picking x's, but we really picked our y's. All right, so just realize that we have our exponential graph, right? Y equals b to the x. We picked our x's and our y's. And in the exponential graph, we picked these, right? We picked the x's. And then we figured out the y's. What we're doing in the logarithm is we are picking up the y's, and we're going to figure out the x's from it. Okay? So let me show you what that looks like. So I think our first question on here is something like, do I want Alex? I don't want Alex. Alex, you can be dismissed for a while. All right. So this is log base 2. All right. And we'll just we'll just work this one. All right. Why not? All right. This is y is equal to log base 2 of x. All right. We're picking our x's. So, and then the equals. Okay. So 2 raised to what power is what? Right? And the answer is the power. So how about I pick a 1 here? Okay. So 2 raised to the first power equals 2. 2 raised to the second power is 4. 2 raised to the third power is 8. All right. How about we do -1, right? 2 raised to the -1 power is half. Okay. How about 0, right? 2 raised to the 0 power is what? Is 1. Okay. So now I have my x's and my y's, and if I had done this a little bit more careful by putting my -1, then 0, then 1, 2, 3, if you just came across this and looked at it, right, I'd look pretty smart. I'd have it -1, 0, 1. No, I wouldn't have that there. If I just had it written like this, and we had -1, or we have not -1/2, just 1/2. Okay, don't do negative there. Okay. So 0, and then we did 1/2, and then we did 1, 2, 4, and 8. And then off to the side, right, I'm like, okay, if I do it this way, see, if all you come across and that's all you see, right, I'm looking pretty good here because it looks like I picked these smartly, right? I was clever when I picked my x's in order to get the y's to come out right. That's not the way it works. You pick the y's and then you figure out what x had to be in order to get to this y. Right. Again, it's an inverse function. That's a good way to think about them. All right. So for that, we could just start graphing. Did I pick any negative x's? No. Well, no, I didn't pick any negative x's. And that's the thing. You can't take the logarithm of a negative number. Okay. So your domain here, x has to be greater than 0. All right. You can't pick a negative number. But my y's went positive and negative, didn't they? So if I'm going to look at my graph, right, we've got positive x's only, but y's are positive and negative. Okay, so all the action is happening in quadrant 1 and quadrant 4. Again, this is a skill that eventually would be nice if you had. I'm never going to quiz you on it. Okay, but it's one of those things where, you know, if you do something like this for your biology class or your physics class and you draw your coordinate system, so like all the action is in the middle of the page, even though you have a coordinate system, your teacher's going to look at this. Wow, you're a smart kid. Yep, that's me. I'm smart. You probably are. I don't know. The reason I say it that way is when I took English Composition 1, I took that class like 6 times. I mean, it was forever that I took that class. And I eventually started taking it at a community college, and I never took it seriously. And I'd kind of mess up somewhere along the way and not be taking it. Right? You know how that works. Pretend that goes through all those points. And I got to the point where it's like, oh, I'm actually getting close to my bachelor's degree. And I originally lived in Pennsylvania. I came out to New Mexico to go to Tech. But I was home for summer, and I was like, okay, well, I'm going to get this done. So I went back to that community college, and I said, okay, we're going to finish it this summer. And that class was like this one. It was brutal. Okay, it was absolutely brutal. It was every day for 6 weeks. We had an assignment like every other day. It was nuts. And I was in that teacher's office almost every afternoon working on a rough draft. And since I was also getting ready for GREs at that point, right? When you study for SATs, you get the little vocabulary words, you drill them. Same thing with GREs. You get your list and you drill them. And then I would use all the fancy words because I was studying for that test. And he's like, wow, you have a really good vocabulary. You must be an A student. Don't say anything. Don't say anything. Don't say anything. Just let them think that. So I say that for you guys, but I don't know. I don't know if you are or you're not. But it is helpful to have your teacher look at you and say, oh, you must be an A student. So that was X. What am I doing here? We are looking at 1/2 1. We have 2, 4, and 8. There we go. So we have 2, and that was there we go. 1, 4, and 8. Hopefully that gave me what I wanted here. All right. Oops. Asymptote. Okay. And there we go. All right. So talking a little bit more about the shape. Okay. Remember when we drew the exponential curve? Beguile, that was the word. He looked at me. He said, wow, you must be an A student. No. Right, what was our domain and range for this stuff? The domain, that was all the x's, right? That was negative infinity to positive infinity. And our range, that was 0 to positive infinity. We had a horizontal asymptote, y equals 0. Well, logarithms are an inverse function. So do you remember what happens with the domain and range in the inverse function? The domain is, right, is this guy here. So here's my domain. 0 to infinity. That's a comma. It's not a negative. Okay, my range right? The range is this guy over here. All right. So the range is negative infinity to positive infinity. And instead of having a horizontal asymptote at y equals 0, we have a vertical asymptote at x equals 0. Okay. So when you're looking at like, well, how do you know what that is? Like, because I know what the inverse looks like. That's why. So we have x equals 0. It always goes to the 0.10, by the way, because something raised to the 0 power is 1. Okay. So the base raised to the 0 power is equal to 1. And the stuff before that is a fraction, right? So it's a negative number, and then stuff after that. Okay. So here's a question: which is bigger, square roots or logarithms? Right? If I put square root and logarithm on the same graph, which one would be bigger? Well, square roots start here, right, and do something like that. But logarithms, 0, 1 here. Logarithms do not get bigger. There might be an intersection in here, but logarithms do not get bigger than square roots. Logarithms grow slower than square roots grow. Okay. So, like if I took the square root of 100, that's 10. If I took the log of 100, that's 2. All right. So even out here at 10, right? Logarithm, the square root function is going to look huge compared to the logarithm. Okay. So logarithms are very, very, very slow growing. But if you let them grow long enough, right? I can take the log of 1 times 10 to the 32. I get 32. Like the log of 1 times 10 to the, pick your favorite biggest number, right? 1 times 10 to 100, I get 100. There's no bound on this. So even though it's slow, okay, it still goes off to infinity. Okay, so if you look at the end behavior, as x goes to infinity, so does y. Same thing with square root. Okay, so let's go ahead and take a look at a couple more problems here. So, all right, graph the function, y equals ln x. Okay, so this one, you know, that's going to be very similar to what we just did. Okay. This is y equals ln x. Here's my x, here's my y. What do you want, right? So this is our equivalent exponential form, right? E to the x is equal to y. So if I plug in x equals 0, right, what are we getting for our y? 1. Okay, let's plug in. Okay, yeah, so well, I don't want to do that. Hold on, all the way around. That's not my equivalent exponential form at all. Right, that's better. Y equals 0, x equals 1. All right, that seems like way too straightforward than what we've been doing. Okay, e to the 1 is equal to e. There's not really a lot to do with this, right? When we do this, right, that's about all we have is saying, well, y is 1, x is e. 2, we have e squared. Let me show you, if you ever want to like nobody should ever ask you like what e squared is, but if they do, okay, here's how you do that. Okay, second function, ln, brings up a little e. You can put any number you want in there. You can put 1. Right? So, oh, it is 2.718281828. Okay. Or you could do, you know, you need to know e squared for some reason. See? It's a delightful number, I'm sure. Or the square root of e. So again, delightful number. 0.5, that's the square root, right? 1/2. So if you ever need the numerical parts of this, that's how you get them. Okay. I think there's a pattern here that you could see, right? How about this side? All right. So once we have established a little bit of a pattern here, I think we could exploit this. Let's see how much it lets us get away with this one. All right. If I was going to do this, right? If I was going to do this, I would want the point x1, y equals 0. Okay. Oops. All right. And then how about we said what? What did we say for y? We wanted to go with y is, or e is, x is e, and then y is 1. Let's see if it lets us do it. Doesn't let us do it. Press an E here. It didn't like it. Really like to have E here. All right. Well, fine. We'll play by their rules. Okay. We'll do the ln, right? Y equals, oh, that's what we could do, right? Let's go back. Fine. You guys are going to be messy about this, right? We have y is equal to ln x. So if we pick x to be 2, right, y would be the natural log of 2. That's how we're going to do it. So fine, we have 2. Oh, and then this one is natural log of 2. All right. 3, natural log of 3. 4, natural log of 4. So fine, that's what we'll do. So let's go ahead and placing the vertical asymptote. Very good. Placing a point. Placing a second point. Okay. If you don't put the little X's there, they make you do the grid. Okay. You can't just put it anywhere you want. You got to do on the grid. Fine. You guys took all the fun out of this. All right. That's similar. Okay, domains. This is another one that gets to be a little bit tough. All right, we'll do maybe 1 or 2 of these, and then we'll call it for the week. Okay. So when you take the logarithm of something, right, the argument here, okay, this argument must be positive. Okay. So it's really important that any x's you feed this thing are positive x's. All right. This only gets positive food here. So when I've got a function looking like 5 minus x, okay, and it doesn't matter any log you want, it's got to be, this always got to be positive. So I need my 5 minus x to be greater than 0. Okay. So let's go ahead and subtract 5 from both sides. We get negative x is greater than negative 5. And I'm going to multiply by negative 1. Do you remember what the rule is when we multiply by negative 1? We get x less than 5, don't we? Because we got to change the sign as we multiply by negative 1. Okay. So any number less than 5 will work. So my interval notation for my domain, negative infinity up to 5. So negative, is that short? Well, what if I plugged in 0? I get log of 5. What if I plugged in negative 5? I get log of 10. So yeah, that's okay. Can I put 0 in there? No, no, you can't put 0 in there. Oops. What am I thinking? Negative infinity up to -5. All right. Oh, +5. Yeah, what am I thinking? All right, up here. All right, not this one. Where was it? This one. Okay, natural log of x squared plus 2. X squared plus 2, right? What's the graph of x squared plus 2 look like? Looks like that. That's always positive. Doesn't matter what x is at all. It's always positive. So for this function, okay, domain, that's everything. Right? So those are the nice ones. Sometimes they give you something like, log of, say, it's a nice easy quadratic to do. How about x squared minus 5x plus 6, right? We could factor that. It's x minus 2, x minus 3. What's the graph of this thing look like? Okay. X squared minus 5x plus 6. X equals -2, x equals -3. Those are my zeros, right? So what's this graph look like? Well, here's my x is -3. Here's -2. All right. And this graph looks something like this. This is a tricky one. I don't think they asked you this one on homework, but this would be a tricky. I would ask this one on exam though. But I used to be able to ask this one on exam because we had paper. I don't think I could do it now. Where is this graph positive? Right? Where is this graph over the x-axis? So the domain here would be -infinity up to 3 union -2 up to positive infinity. All right. So if we had to do a logarithm of x squared minus 5x plus 6, let me show you. All right. The worst with this thing. Okay, we do Desmos. There we go. All right. Just put Desmos up just because I always use Desmos. What are you doing? Don't, not searching. We have y is equal to log, doesn't matter which kind. Minus 5x plus 6. Oh, I got the other side here. I'm sorry. I should have been more careful with my signs. X is 2, x is 3. This was the wrong side. X equals 2, x equals 3. 1, 2, 3. Here's my parabola. So my domain is either, right, -infinity up to 2, union 3 up to positive infinity. And if I look at my Desmos graph, right, you can see there's a gaping hole between 2 and 3. Okay, there's a gaping hole. Here's 2, here's 3, and then there's our domain for our function. Okay, and it does that. So that was the beginning part of logarithms. We will certainly come back and revisit this next week. Not next week, the week after that. Next week we'll be starting on a review. I have to do 2 things for you. At the end here, I've got to put in a quiz that lets you deal with respondus inside of this, and then so we could work out our problems. And then we've got to put in our exam, and I've got to work out respondus and connect. So that's on me, and I'll sort that out. Okay. So let's give it a call there, and it's Thursday, isn't it? It's Thursday. Holy cow! So Thursday, you guys have a great week. Go ahead and stop. recording here.